Hello, everyone, and thank you for joining. My name is Beyza Dahan, and I am an undergraduate student in mechanical engineering. Today, I'll present our project titled Integrated Microfluidic Chip Platform for Cyclotide Isolation from Plant Extract. This work was conducted as part of a multidisciplinary research project supported by IBU Scientific Research Projects Coordination. The aim of the study is to develop a microfluidic platform that integrates two different molecular isolation techniques, electrolysis and membrane-based filtration. By using microfluidic chips, we target a more compact, faster, and cost-effective alternative to traditional methods like HPLC. To achieve this, we designed, fabricated, and tested two chip types. The E-chip, which uses electrodes for electrochemical separation, and the MEM chip, which uses a physical membrane for selective diffusion. Electrolysis is a method that uses electric current to derive chemical reactions in a solution containing ions. By applying voltage across two electrodes submerged in the solution, we can move or transform specific charged molecules in our chip. This principle allows the manipulation and potential separation of target compounds. Membrane-based separation relies on a semi-permeable barrier that allows smaller molecules to pass while blocking larger ones. It is commonly driven by pressure or concentration gradients. In our system, the membrane enables chemical interaction between two flow channels without physically mixing. The E-chip includes three microchannels fabricated in PDMS. These channels are bonded onto glass slides that are coated with conductive material. These glass slides are coated by enabling different mask designs for layer deposition. Masks for the coatings were created via laser cutting. After all glass slides were thoroughly cleaned with isopropanol, acetone, and rinsed with deionized water and dried with nitrogen, they are sent for sputtering process. There were three batches done for this objective. The first batch was ITO coating with RF supply, second batch was ITO coating with DC supply, and the third batch was aluminum coating. The chip was designed in AutoCAD and manufactured using a 3D mold. It has two parallel PDMS channels. The lower channel has 200 micrometer depth, 1 mm width, and 25 mm length. Upper channel has 1 mm depth, 1 mm width, and 25 mm length. A pair has been sent for ITO coating with DC. PDMS were cleaned with isopropanol and acetone before the operation. To validate chip quality and surface coatings, we have used optical profilometer for measuring coating thickness and surface roughness, scanning electron microscope for detailed visualization of coating uniformity, digital and inverted microscopes for observing chip flow during testing. Softography steps for the chip production include silicon and a binder solution added to a container at ratio of 1 to 10. They are mixed for 3 minutes. The mixture was then poured onto wafer for each chip and 3D mold for the MEM chip. Wafer and 3D mold were placed in a desiccator to remove air bubbles for around 40 minutes. After that, it is kept on a hot plate at 60 degrees for 1 hour. After the 1 hour, the chips are cut out from their containers. Holes are drilled for the inlets and outlets via 1 millimeter punch. The production of the MEM chip is done at this step. For each chip, a little cut from the sides is done for electrical connection, and then O2 plasma method was used to bond three-channel PDMS to the surface of the coated slides. Wires are connected to the open sides with epoxy and the E-chip is ready for experimentation. The E-chip was tested by introducing three fluids through its three inlets. 8.5 pH buffer from the first inlet, a solution of methanol, chloroform, and plant extract from the second inlet, a phosphoric acid mixture from the third inlet. A voltage of 3 volts was applied. Samples were collected from each outlet separately and they are labeled accordingly. For the MemChip experimental setup, it has two PDMS channels, upper and lower. With a PET membrane in between, this structure allows selective molecule exchange between the channels. The assembled chip is compressed between two PMMA plates using bolts and nuts, providing mechanical strength and leak resistance. The MEM chip was operated without voltage and used plant extract solutions at three different pH levels at 3, 5.8, and 7.6. And they have used different flow rates 1, 1.5, and 2 microliters per minute. The aim was to observe the effect of the pH and flow rate to the separation process. Each pH was tested at three different flow rates. Samples were collected and labeled from both outlets after every experiment. In two batches of ITO coating, first one with RF was conducted while the second one with DC wasn't. The first thought reason behind that is while RF was done for 6 hours, DC was done for only 2 hours, and the sputtering machine broke and stopped working afterwards. To see the difference in both coatings, they were measured under the profillometer and SEM. Using the profillometer, we measure the thickness and roughness of the ITO coatings. First coating done by RF's power supply when measured in profillometer showed that the coating mostly evenly distributed over the glass slide. The gap for the flow channel is permanent. It shows a thickness between 600 nanometers and 700 nanometers. In the optical profillometer, the results of the second coating did not come out as desired. It is thought that this is due to the transparency of the second coating. The thickness cannot be easily made out from the profillometer as the reading was faulty. SEM image of the first coating shows that the channel gap is getting narrower. This indicated that there was a leakage under the mask in the sputtering process. For the second coating, the channel gap is not as prominent as the first coating. This could be attributed to its thinner ITO layer. There is not enough material to show a deep channel. When the coating thickness was measured in SCM, it is seen that the first coating is 3 times thicker than the second coating, which was expected as it was coated 3 times longer. Non-conductive nature of the second coating can be attributed to its thin layer. In the surface SCM image, we can see that the RF coating has bigger group sizes than DC coating, which shows that the coatings had different structures depending on the sputtering conditions. A pair of man-chip specimens were put under the sputtering with the second batch of ITO. It was planned to use as a way to mash up two separation techniques, but the layer wasn't conductive. Under the inverted microscope images, if we take a closer look between an ITO coated PDMS chip and a non-coated PDMS chip, it can be seen that there are rough textures on the surface of the PDMS cast. While the ITO layer coated the valleys on the surface, it wasn't enough to cover the entirety of the chip, which resulted in uneven layering, causing non-conductive coating. Under the profillometer, it can be seen that the roughness of the PDMS surface caused some peaks and valleys in the coating. While some points are in between 400 nanometers and 500 nanometers, most of them are lower than 200 nanometers. So the future work on PDMS, the layers should be thicker than 300 nanometers while the plateaus can be seen. For the conclusion, we have successfully fabricated both types of microfluidic chips. During the process, we encountered issues with ITO coatings with inconsistent conductivity. Because of that, we shifted to aluminum coatings. We were able to integrate both electrochemical separation and membrane-based filtration into our chip design. This dual approach allowed us to explore two distinct isolation mechanisms on the microscale. After running our tests, we collected the samples and sent them to HPLC analysis to evaluate the actual separation performance. We are waiting for the evaluation results. Lastly, our surface characterization using the profillometer and SCM provided valuable feedback. They helped us understand what to watch out for in the future designs.